So hi and welcome to my presentation about blacksmith, scalable rowhammering in the frequency domain. My name is Patrick and I'm a PhD student in the computer security group at ETH Zurich. And this work, blacksmith, has been joint work with Qualcomm and V Amsterdam. So our talk has two parts. In the first part, I will talk about blacksmith, which is a Rowhammer fuzzer. So I will explain how you can create a primitive that allows you to trigger bit flips in memory. And in the second part, my colleague Stijn will show you how you can use these bit flips to exploit a system. So let's get started. So first, I will give you a brief summary. So our work is motivated by the claim from DRAM manufacturers who promised that the DRAM devices are Rowhammer free. So for example, Samsung promised in their general assembly presentation that they have now Rowhammer free devices that consume less power and have more performance. And also Micron mentions it in their product specifications that the devices are Rowhammer free. However, we show in our work that we can craft novel frequency-based Rowhammer access pattern that allow to bypass all currently deployed mitigations on DDR4 devices. And for that, we build a fuzzer named Blacksmith that uses these new patterns and allows large-scale testing of DRAM devices. And our work also provides novel insights about mitigations and the patterns found by Blacksmith. And using Blacksmith, we show that the TRR mitigations on all PC DDR4 devices and also LPDDR4X devices are broken. So before starting about talking about Blacksmith, let me quickly give you a brief background on DRAM. So I guess everybody of you knows DRAM, dynamic random access memory, that is today widely used in many different devices, for example, servers and also notebooks, smartphones, smartwatches. And here you can see a PC DIMM equipped with 8 DDR4 DRAM chips. And each of these chips contains multiple DRAM banks. And these banks are organized in a matrix-like structure consisting of rows and columns. And each DRAM cell consists of an access transistor and a capacitor and holds a single bit. And due to the dynamic nature of DRAM, it is required that you refresh these cells because the capacitors leak charge and then they forget the data that is stored. And hence it is necessary to refresh these rows. For example, each row every 64 milliseconds in DDR4. And to get an idea how a Rowhammer works, you have to know how DRAM works. And for that, let me show you how a write operation works on a DRAM device. So reading and writing always happens row-wise. So for example, if you want to read the row in the top, so the green one here, so what we would first do is to send a DRAM activate command. And then this row gets loaded into the row buffer. So this happens usually transparently. In the CPU, there's a memory controller that basically translates your access request. So if you access memory in a program into these DRAM commands. And after this row has been activated and is loaded into the row buffer, you can, for example, do a write and modify the values. And after that, before you access another row, you have to issue a pre-charge command that writes back the modified data. And let's see how this mechanism can be exploited by Rowhammer. So the Rowhammer effect has been discovered in 2012 for the first time. And the idea basically is that we exploit the leaking charges of the capacitors. So what we basically have to do is activate 2 rows. So here, the red one and the other one with one victim row in between. So these 2 reds are called aggressor rows and the one the victim row. And if we do these accesses repeatedly many times over and over again, then these aggressor rows will leak charges, which will impact the data that is stored in the row in between the victim row. And at some point, if you repeat this often enough, you will see bit flips in the row in between. And there have been many different Rowhammer access patterns proposed by academia in the past. So this one here is called double-sided because you have 2 aggressor rows with 1 victim row in between. And there are other patterns that I will discuss later. So now you may ask, okay, this sounds very theoretically, but what can we actually do with it? And there has been a plethora of work that showed that these attacks are really practical. So for example, you can exploit across VMs applications that run on the same host. It has been shown that you can also run Rowhammer on smartphones. So smartphones have usually LPDDR memory. Even over the network, so there is RDMA basically that allows to access memory directly via the network card, and you can use RDMA to Rowhammer the DRAM device, assuming that your network is fast enough. Then it has been shown that also Rowhammer works on devices that employ ECC. So ECC memory is usually used in servers, and also over the network, over in the browser via JavaScript. And now the research question that motivates our research are basically the claim from DRAM manufacturers that promise that the DDR4 devices are Rowhammer free. So there was work before in 2020 called Trespass that investigated these mitigation mechanisms on the DRAM device called target row refresh for the first time. And they found out that TRR, so this mitigation mechanism, is like an umbrella term for different mitigations. So different manufacturers deploy different mitigations. And they could show that if you modify the existing patterns a bit, then you can still trigger on around 30% of the DDR4 devices Rowhammer bit flips. And for that, they used so-called n-sided patterns, which is a generalization of the double-sided pattern. I will show you an example later. And given this work, we asked ourselves if the majority of today's DDR4 devices are indeed safe against Rowhammer, or if we can build better patterns to bypass these mitigations. And then given that, also if these currently deployed mitigations have weak spots that we could exploit. So and the typical approach used by previous work is reverse engineering, to understand how the deployed mitigation works to mount a Rowhammer attack. And the problem with this approach is that it's very time intensive. So usually you design experiments to figure out certain properties of the mitigation, and this makes this approach not scalable if you want to look at many different devices. And also it provides only limited insights that may not be transferable among devices, because we have seen in existing work that the manufacturers might change their mitigation, for example, across different devices or device generations. So the insight that you gain is quite limited. And to give you a better understanding about Rowhammer, let me illustrate the problem from an attacker's perspective. So I mentioned before that DRAM is dynamic, right? That you have to refresh these rows in order not to lose the information. And it is a synchronous protocol, which means that all commands must adhere to specific timing requirements. And each cell in a DRAM device must retain the information for 64 milliseconds. So you can see a timeline that represents this refresh window of 64 milliseconds. And to refresh each of the DRAM rows in that 64 milliseconds, you must send around 8K refresh commands. So each of these refresh commands refreshes some of these rows in the DRAM device. And we can issue around 166 activations. So what I showed before, when you load a DRAM row into a row buffer, in between of two refresh commands. So this is basically the space that the attacker has, right? Because after these 64 milliseconds, the row will be refreshed. So if you are not able to trigger the bit flip within this period, then it's basically over. So from the attacker's perspective, we have basically 1.3 million activations. And depending on how vulnerable the device is, we need around 10K and 147.5K activations to a row to trigger a bit flip. That's what I showed before, that you have to repeat hammering many times so that enough of these charges, of these leaking charges, accumulate to trigger a bit flip. So, and now what basically existing patterns do is they craft a pattern, for example, a double-sided pattern, and then they repeat hammering this pattern over and over again. And what we asked is basically if there is a way to craft patterns in a more effective way to bypass the mitigations. And now let's switch over to the defender's perspective to give an idea how these devices usually protect against Rowhammer. So here you can see how a deterministic mitigation works. So the idea is that we have a component called sampler that basically samples some of these accesses, of these activate commands, and then has a kind of counter that keeps track of how often these different rows have been activated. And if the counter reaches a certain threshold, then you have to preventively refresh the row, right, before it can trigger a bit flip. And I mentioned before that this DRAM is a synchronous protocol. This means that we can only send a refresh at certain points in time. So at the refresh time, then there is an inhibitor component that basically looks up into the table if any of the rows reach this threshold, and then sends a TRR. So refreshes this row before it can trigger any bit flips. And this problem can be translated to the frequent item count problem, which is well studied in literature. But the problem is that it's very hard to solve this in DRAM because there are many constraints. For example, the area is quite limited in a DRAM device, in a DRAM chip. Then there are these timing constraints that I mentioned before. So you cannot send these additional refreshes, these TRRs, at any time, but only at refresh times. And also, of course, costs like performance, for example, or energy consumption must be taken into account. So, and now back to the question how we can craft more effective patterns. So we looked into existing patterns. So here are three very prominent examples. So we have the single-sided pattern where we hammer here row X and then might see bit flips in one of those. We need another row somewhere apart to evict this row from the row buffer, right? And then we have the double-sided that I explained before, and we have, for example, a four-sided. You can see this is basically just an extension of the double-sided pattern. And four-sided is an example for an n-sided pattern with n equals 4. And we made the observation that in these patterns, all the aggressors are hammered uniformly, so the same number of times. And this is a very simple case for the mitigation, right? Because if it knows, if it can track one of those, then it already knows the hammer count of the other ones. So this was our first insight. And we wanted to see how effective it is if we use non-uniform access patterns to bypass the mitigations. And for that, we constructed two experiments. So in the first experiment, what we basically do is we take an n-sided pattern, for example, a 6-sided, and then at random repetitions of the pattern, we just access another double-sided aggressor pair, so two other rows. And then basically these two other rows will have a non-uniform hammer count at the end. And in the other experiment, we just have random patterns, so random rows, and then at some randomly picked locations of where we repeat the pattern, we just access a double-sided aggressor pair. And to evaluate how good this approach works, we bought some DDR4 devices, so 40 in total. We tried to have a very diverse set of devices from different manufacturing dates with different frequencies, sizes, and also ranks. And from the three major DRAM manufacturers, Samsung, Hynix, and Micron. We also had 4 devices where we couldn't identify the chip manufacturer. But the device is from Kingston. We're from Kingston. And here you can see how this looks like. So we have these very different devices. Some of them were like gamer DRAM devices with heat spreaders. And this is our test cluster where we evaluated our experiments. So we used a very common platform, normal PC platform with an Intel i7 8700K. Running on Ubuntu. And here you can see the results of our first experiment. So here we only report the devices where we could trigger bit flips at all. So in the first column, you can see the results for trespass for the existing patterns that were proposed by literature before. In the middle, these n-sided with a bit of non-uniformity, and in the last column, these fully random patterns. And what we could observe here in this experiment is that on some devices, it's really important to have this non-uniformity to bypass the mitigation. But what we could also see on the other side, on some devices, only uniform pattern worked. So this was our first observation, that non-uniformity leads to bit flips on some DIMMs where previous n-sided patterns failed to trigger any bit flips. And starting from this first observation, we wanted to reduce the search space further, right? So now we have one property basically that allows us to find more bit flips on some devices, but still the search space is very huge. So we designed some more experiments to figure out what is very important to effectively bypass the mitigations. And in the first experiment, we asked ourselves, when should we hammer an aggressor? So here you can see a pattern with 2 rows, and here some other random rows. So they do not matter here. And the idea is basically we hammer these 2, then we have some other accesses until we observe a refresh. So you can observe this by a high memory latency. And then we again repeat hammering these 2 and the other ones, the random ones. And we repeat this for like 1 million activations. And then we check if we see any bit flip. And then we repeat the same experiment, but shifted by 1. So we have 1 access before, then our double-sided aggressor pair, and then until the next refresh, random accesses to rows. And we do this systematically for all different possible offsets in the pattern. And then we check for bit flips. And what we could see in the experiment is that only if we hammer our double-sided aggressor pair at very specific times, we could trigger bit flips. And the reason for that is that the sampler might not be active all the time. So it might only sample specific accesses. And as here is already the next refresh, it might be that the sampler is not active here anymore, cannot capture these accesses. So our next observation is basically that it's very important when we access the aggressors in a pattern. And this allows us to bypass the mitigations more effectively. And here we can see some data from an experiment from a real device, from a Samsung DIMM. And you can see, so if this is the pattern length, 100 accesses, then only if we hammer at the end, we can trigger bit flips. And also not at every offset, right? So there are some points when we hammer there, then we also don't see bit flips. And this suggests that the sampler is active at these points and also here at the beginning. Based on that, we constructed a next experiment. We wanted to know for how long we should hammer an aggressor. So as I mentioned before, this Rowhammer phenomenon is based on leaking charges. So if you hammer a longer time, you will leak more charges and you will see more bit flips. But at some point, if you hammer too much, it might be that you get caught by the mitigation. And that's why we wanted to know for how long should we hammer an aggressor. So we start again with the same experiment like before, where we have our double-sided aggressor pair and then some random accesses. But now additionally to just hammering the aggressor pair once, we also try different intensities. So we repeat, for example, hammering 2 times or 3 times and so on, up to the whole refresh interval. And we try this for the different offsets in the pattern. And then we again check if we could observe bit flips. And what we found is that for some point you can increase the intensity and see more bit flips. But if you get over this point, then you don't see bit flips anymore, which suggests again that the mitigation caught these accesses and then refreshed these rows before any bit flips could be induced. And this is basically our next observation, that up to a sweet spot, we can increase the hammering intensity to see more bit flips. And then after that, the number of bit flips drops. And here again, we have some real data. So here we can see the number of bit flips and the aggressor offset, so where we hammer in the pattern. for an intensity of 1, so we only hammer the aggressor once. And here for an intensity of 2, and we did this for different intensities. And one interesting point is, for example, this here you can see that if you hammer 2 times, you get way more bit flips than if you hammer 4 times. So this indicates that at some of these repetitions, you get caught by the mitigation. And then the last experiment that we conducted is if our pattern should be longer than 1 refresh interval. So previous patterns were quite short, for example, double-sided or 4-sided or 6-sided. And we wanted to know if it makes sense from perspective from the attacker to have patterns that are longer. So what does it mean? So instead of just building a pattern that is 1 refresh interval long, we build patterns that are longer, for example, 2 refresh intervals. And we do this by basically just extending the previous experiment. So instead of just limiting the pattern length to 1, we also make it longer than 1. And then you see that there are some patterns where we hammer, for example, 1 refresh interval a lot, but then the other one, nothing. And then we do this the same again with the shifting of the offset that we start later, and then we repeat the same basically. And here we could see that it makes sense to only hammer in some of the refresh intervals. That is more effective to bypass the mitigation. And this is our last observation, that hammering patterns, hammering with longer patterns, longer than 1 refresh interval, is effective on some of the devices to bypass the mitigations. And here again, I have some real data. So here you can see, so this part is basically 1 refresh interval, and you see only like very few bit flips. But then if you extend the pattern to 2 or 3 refresh intervals, then you see many more bit flips. And based on these 4 observations, we came up with a general model to describe this new class of patterns. We found out that the concept of frequency, phase, and amplitude nicely match to these properties. For example, the phase when we hammer a pattern, so at which location, and then the frequency, how often we repeat hammering, and the amplitude, how intense we hammer the aggressors. And now the question is, how can we determine effective parameter values? So because these concepts basically are very dependent on the deployed mitigation. So different devices might require different amplitude, phase, and frequency to trigger bit flips. And for the implementation, our goals were to have a solution that is scalable. So we wanted to have like a plug-and-play solution that allows large-scale testing on many different devices, and also something generic that can cover many different TRR implementations. And last but not least, also something that is extensible, because it might be that DRAM vendors made tiny changes, and we want to have a solution that allows to really thoroughly test the mitigations. And for this, we built the Blacksmith Rowhammer Fuzzer. And the basic idea of Blacksmith is that you have these 3 parameters, frequency, phase, and amplitude. And they are defined over ranges that we determined experimentally. And then we built a pattern where each of the different aggressor pairs has a different set of these values. And combining them into one pattern allows us basically to brute force these parameters more effectively. Then we hammer the pattern, so we execute it many times over and over again. And then we check in the memory that we have initialized before if any of the data changed. And then basically, based on the location where the change happened, we can figure out which of these different aggressor pairs triggered a bit flip. And we repeat this for a few hours, for 12 hours in total on the device of our test pool. And then we get the following data. So we found out that all devices are vulnerable. With our approach, we could trigger bit flips on all 40 devices of our test pool. And previous work, so Trespass, only could trigger on 15 or 40 devices bit flips. And we also found out that the devices are quite vulnerable, more than reported previously. So on some devices from Samsung, we could trigger 36,000 bit flips. And this has impact on the exploitability, because more bit flips means that it's easier to use these bit flips to exploit the system. We also analyzed the exploitability with these new bit flips. And we found out, for example, that a PTE exploit that has been proposed in existing work works on 30 or 40 devices within 3 seconds and 2 hours and 8 minutes. And then there's also a more difficult pseudo exploit that basically targets the pseudo binary. And this also worked on 15 or 40 devices. And to summarize the PC results, we can say that all of PC DDR4 devices are vulnerable to Rowhammer, and that the DIMMs are even weaker than reported before. And these new results indicate that exploitation is even easier than assumed before. And we also did some experiments on LPDDR4X, so on the DRAM that is used, for example, in smartphones, but also on laptops. And we found effective patterns on 16 of 19 devices. You can see also a significant number of bit flips on some of the devices. And on 3 devices, you can see we didn't find anything initially, but then we reverse engineered those devices, basically by designing some experiments and figuring out how these mitigations work. And we found out that if we slightly change the parameters of our fuzzer, we can also find bit flips in reasonable time, so in less than 3 hours. And this again shows that all LPDDR4X devices are broken, that the chips are also weaker than before. So here you can see like 12 million bit flips, and this also has impact again on the exploitation. And based on the insights, based on these new patterns that we found, we also derived some novel insights. So we found out that on some DIMMs, the patterns are quite sophisticated, complex, and very difficult to craft them manually. We also found out that these TRR mitigations are chip dependent. So on some devices, we could only trigger bit flips on a very specific byte offset. You have to know that usually these chips on the DRAM device work all in parallel, meaning that if you only see a bit flip at a specific byte offset, then only a specific bit is vulnerable. Specific chip is vulnerable to Rowhammer. And we also did some experiments to figure out the sampler size. So how many of these aggressors the device can keep track of. And we figured out that most of the devices only can keep track of less than 30 aggressors. So we also disclosed our findings, reported it to the National Cybersecurity Switzerland. We got a CVE assigned and disclosed our vulnerability in November of last year. So to conclude the first part of the talk, so Blacksmith is a very effective and scalable way to trigger bit flips. And we show that all current TRR mitigations are vulnerable. And we also can say that the approach generalizes well. So for example, we received DRAM devices from another vendor that we haven't seen before, and Blacksmith was able to find working patterns on them. And this work shows that we need really principled mitigations with provable security guarantees instead of the obscure proprietary mitigations that the DRAM vendors use today. So this is the end of my talk. Thank you very much for your attention. Are there any questions? A bit more time, right?
Hello, thanks for the very nice talk. It was very interesting to see all this. I have just a question, and it's regarding if you can go back to slide 29, for example, where you had all those access patterns. Yeah, this, for example. So for me, it's like black magic. Like, how can you detect when the reverse signal is being triggered? Because this is just handled by the low-level reverse circuitry, right? So yeah. How do you know that? And how can you align those accesses properly?
You can measure, so for the refresh, you can measure the access latency. You will see that when a refresh happens, the access latency has like a peak, and then you can detect when the refresh happened. And for the addressing, so this part, I skipped before because there is existing work that shows basically how you can use bank conflicts as a side channel to reverse engineer these addressing functions. So the memory controller has some proprietary, non-disclosed addressing function that basically translate the physical address into a DRAM address. So consisting of bank, row, and column. And using this bank conflict sidechain, you can figure them out, and then you can really precisely address specific rows and then build your pattern, like, for example, in this double-sided fashion where you have one victim row in between.
Hello, hi. Very nice talk. Thank you for your contribution. So, would you be able to know if you had a double flip?
Yeah.
Which means no actual change in the output.
Ah, you mean that it flips twice? No, you won't see this. But it could be that you have in one row multiple bit flips. This could happen. And also the direction is depends on the data in the rows adjacent. So it could be that it flips from 0 to 1 or from 1 to 0.
What is the most frequent? 0, 1 or 1, 0?
Depends on the data pattern. But we use a random one. Yeah. But there are existing work that characterizes basically these different data patterns and the impact.
Yeah, I'm familiar with the literature. So the initial pattern that you put, do you also variate that? I mean, the way you load the RAM before hammering it also is going to change the bits you are going to hammer, you know? So do you have like specific patterns for every byte or something like that you used that worked better on some models or something like that?
We didn't look into that, but we only used a random pattern, basically pseudo-random, so that we can reconstruct it and check if bit flips happened.
Okay. Yeah, I mean, if you look at previous literature, people may have been more successful with AA instead of FF, for example.
Yeah.
The reason is unknown to me too, but it could be related to the chip construction, for example.
Yeah. That's definitely one thing that we want to look more into. Yeah.
Other questions? Hi, beautiful graphics, very nice talk. I just wonder, is this like physically destructive? Have you bricked like a shit ton of RAM sticks, or like can you do this millions of times and the memory will like survive?
So the worst thing that can happen during the execution is that the system crashes. Depends on where you do your Rowhammer attack. So in our case, it was really about finding the patterns, right? So what we did is just allocate a super page, and the super page is then only used by our application, right? And then we could hammer there. But it could be, of course, that if you do a real Rowhammer attack and you have other data around, that you break something from the system. And then there's this other aspect. If basically the devices wear off, if you do Rowhammer attacks many times over and over again. And as far as I know, there's no existing work looking into that, because it's very difficult to analyze this, basically, right? You would have to buy many DRAM devices and then let it run for months or years maybe, and then look into Rowhammer vulnerability. Yeah. But it could well be, right? Because of physical phenomenon, and yeah.
Other questions?
So do you have any thoughts or ideas on what would be a good mitigation or solution to Rowhammer, or is this something different that you're not familiar with?
Yes, there have been many proposals in academia. One of those proposals comes actually from my group, from a colleague of mine. That's a mitigation called ProTRR that basically is the first in DRAM mitigation. So it's really in the DRAM chip and comes with provable security guarantees. So my colleague basically built a formal model showing that this mitigation is safe against any kind of Rowhammer attack. So he constructed what could be considered the best theoretical attack, and then showed that the mitigation can withstand it.
And this formal model is like modeling the actual physics of DRAM and proving things about that?
No, modeling basically how Rowhammer works, right? That you have to activate a row a certain number of times, and then that there's a distance. So he also takes physical effects into account, like the distance. So actually one thing that I did not highlight in my talk is that if you hammer, so let me show you quickly the slide. Yeah, so if you hammer these two aggressor rows, these red ones, then it might not only impact the one in the middle, but also the one on here outside, and not only with distance 1, but also a higher distance. This is, for example, due to the physical effect, right? The leaking charges. And this, for example, Protea R also takes into account.
Okay.
Other questions? Okay, so I guess I will continue. And thanks for the talk.
Okay. So essentially what Patrick has just showed you is that we've built Blacksmith, and we can use Blacksmith to find patterns that are effective and that allow us to flip bits at certain locations in physical memory. Now you might be wondering, right, why do I care? Okay, it might not be nice, but can an attacker actually leverage bit flips like these to break security guarantees of my system or do nasty things to my applications or my data? And the answer, perhaps unsurprisingly, is yes. So what I'll be doing in the remainder of this presentation is I'll be showing you one example of one such attack. You may have briefly seen this also highlighted in the evaluation of Blacksmith, but this concerns a paper, Flip Feng Shui, Hammering a Needle in a Software Stack. It was first introduced in 2016 by Kaveh and Ben Gras, among others. Kaveh is a member of our group. And essentially, what this paper does, or what this work does, what Flip Feng Shui does, is it's a technique in a situation where we have two VMs on one virtualization host, right? So we have a victim VM, and we have an attacker VM. And what this technique allows us to do is it allows us to break CPU virtualization isolation by flipping one bit in a memory page, physical memory page, in our co-hosted victim VM. Okay. When can we do this? So what are the assumptions we have to make on the system? Well, first, we have, of course, we require that we have a victim and attacker VM that are co-hosted. We also have to have the ability to flip bits in physical memory, right? So it has to be a DRAM device that is vulnerable to Rowhammer. Well, happily, Blacksmith has shown that there are lots of such devices. We have to have memory duplication enabled on the host. We'll see the why and how of this later. And also, not unimportantly, we have to know the content of the page. So we have to know the content of the memory in which we're going to cast a bit flip beforehand. So, okay, if those guarantees are met, how do we actually perform the attack? Flip Feng Shui presents a more general model in which a hardware vulnerability is combined with a physical memory massaging primitive in order to flip the bit we mentioned. In this presentation, however, we'll be focusing on just one specific instance that's also highlighted in the paper, and we're going to use hardware, or we're going to use Rowhammer as the memory glitch, and we're going to see a technique called deduplication as the memory massaging primitive. Now, why is this massaging primitive necessary? Is you have to remember that in Rowhammer, not all locations in DRAM are equally vulnerable. And there is no guarantee that the bit flip you want to cause, right, that this location in physical memory is actually occupied by data where you want to cause your bit flip. So what you need is you need the ability to move around a victim page. You need the ability to move around victim memory in physical memory to get it to a spot where you can use a Blacksmith pattern. And memory deduplication, as we'll see in a minute, is a technique that we can employ to actually get our victim VM page backed by physical memory of our choosing to a reasonable extent. So how does this mechanic work? Well, first let me talk about deduplication as a technique. It's basically, you have to imagine that a virtualization host that virtualizes many VMs, that these VMs have pages, have ranges of memory that they share, that have the same contents, and that it would be an enormous waste of physical memory, and therefore added cost to, say, cloud providers, if each of those copies would have to be backed by separate sections of physical memory. So what a kernel like Linux does, for example, is it employs a technique called kernel same page merging, and it starts to scan host physical memory. So it scans the range of physical memory, and it's on the lookout for pages, for regions of memory that contain the exact same content. And if it finds pages like these, then what it decides to do is, okay, I'm going to unmap one of those pages, and I'm going to instead map it to the same location in physical memory that the other VM is using, thereby sparing a lot of physical memory in the process. What is important in this context, of course, is that if we were to change any of the data in our VM, then the kernel employs something called copy on write to ensure that those changes aren't replicated in the victim VM. This is, of course, necessary to maintain the semantics of this entire operation, but also any other alternative would be a nightmare from a security point of view, if you could just arbitrarily write to victim memory, right? However, it's important, of course, for the CPU or the kernel to employ a copy on write or to use this technique, that it needs to be able to detect that we've written to a page in the first place. Now enter Rowhammer. Where can deduplication go wrong? Well, we return to the situation here where we have merged pages, and both the victim VM memory page and the attacker VM page are backed by physical memory chosen by our attacker. Now, what happens if we flip a bit? We only have a change in host physical memory, and it's totally oblivious, right? The CPU doesn't notice it, the kernel doesn't notice this, because if it would notice this, if it would be able to detect such bit flips, well, it would be trivial to undo them, right? And bit flips wouldn't be nearly as much of a problem. So because it doesn't notice this, what happens is that these changes are visible from both the attacker VM memory and the victim VM memory, right? And that's why this combination of deduplication and Rowhammer is so dangerous, because we can essentially get a victim VM memory page backed by physical memory of our choosing, and then we can use Rowhammer and Blacksmith as a fuzzer to flip a bit in this physical page without the CPU or the kernel noticing anything, and thus also flipping a bit in memory used by the victim. So what we're going to do is we're going to use this technique to construct an attack against OpenSSH. So imagine the following scene. All right, we have a victim VM is running an OpenSSH server, and our victim has an RSA public-private key pair. The public key is in the authorized key list in the victim VM, and the victim uses his private key to authenticate himself to the server and to gain access. Now, how can we leverage Flip Feng Shui and Rowhammer to break into this VM to gain access to this server without actually having access to the private key? If you were to look at what OpenSSH does, if someone tries to connect, if someone tries to SSH into your server, there's this file called authorized keys, which basically contains entries like these. It's a list of public keys that are authorized to access the server. And what you can see is if you drop the prefix and the comment in one of these entries, and then you do a base64 decode, is that what this really contains is just 3 length prefix fields. We have a constant string indicating the type of the key. We have a public exponent in RSA, which is typically set to the static value of 2 to the power of 16 plus 1. And then finally, we have an RSA modulus, which is the product of 2 primes. Just to recap, for those unfamiliar, we have an RSA public key is, as I mentioned, this modulus and this public exponent. We also have a corresponding private key, which basically also holds this modulus on the condition, of course, that the person who owns the private key is aware of the 2 prime factors of the prime factorization. And he also has a private exponent D, which is derived from these factors and from E. And now what you need to imagine is what happens if we flip a bit in this modulus N. Well, as it turns out, N prime is easier to factorize. So the paper contains some math which I'll not go into here, but essentially in between 12 and 22% of cases, we can factorize this new n prime effectively. And if we can factorize n prime, well, we can compute d prime. So we can find and construct a private key that allows us to gain access to a server that's using the modified public key with the bit flip. Okay, so what's our game plan? What's our exploitation plan? Basically, first, we have a stage of templating. And in templating, what we're doing is we're using Blacksmith to find locations in physical memory where we can reliably flip a bit, right? And then we use our memory deduplication technique, our massaging, to get the victim public key into the physical memory location where we can flip a bit. And then finally, we flip a bit in the keys modulus by using the Blacksmith pattern that we found on the physical memory we've selected and where we've moved the public key. Once this is done, the victim VM is only aware of this modified public key. We can construct our private key and we can gain access to the server. Now, what does this look like from a memory point of view? You have to imagine that the attacker is, of course, aware of the victim's public key because it's, well, public. And it places this somewhere in its memory where we can cause a bit flip. And next, what the attacker wants to do is it wants to get the victim to load a copy of this public key into its memory so that next KSM can do its scan and can merge these pages. Now, one technique, for example, that the attacker can employ is it can just try to SSH into the victim with an invalid or with a wrong private key, which will cause SSH, or OpenSSH, to load the authorized keys file because it needs to check, okay, is this private key corresponding to any authorized public key? And then the Linux page cache will take care of the fact that it's located in memory, which allows KSM, which gives KSM the opportunity to merge the pages. And now, voila, we have the victim VM page backed by physical memory of our choosing, and we can flip the bit. A B turned into a C here. We flipped the bit. We've modified the public key. This change also is visible from the victim VM. And if we now try to use a modified private key on the victim, we will have gained access to this server. Now, to drive the point home a little, we have a demo. It's a pre-recorded demo. We weren't brave enough, now that we have enough time to try this live. Let me quickly. Here. Yeah. Right. The green thing. Right. So basically, what this demo will show you, it's intended for another project, but it's using the same technique, and I'll be pausing at some places during the demo to showcase some important details. So what's happening here is we've created our VMs, and we've generated a public key for our victim. And we've highlighted here a small part of this key, because this is the part of the key, right, node PSJRS, where we're going to cause a bit flip. Now that we have basically set this up, the next step is going to be to start our Blacksmith fuzzer, or to start our end-to-end exploit rather. And what we're going to do is first we're going to have to reverse engineer some parts of DRAM, which is the first thing you'll be seeing in a minute. Right, so we have started the exploit. And the first thing we're going to do is we're going to reverse engineer some aspects of the DRAM organization, which we'll need to run the fuzzer. That's what's happening here. And once this reverse engineering is done, we can start our templating phase. Essentially what this means is that we are going to start generating patterns at different locations, and we're going to try these patterns out until we've hit a pattern that's both effective enough and that results, if applied, in a public key that we can actually factorize the modulus, right? So what we've done now is we're starting to try, it's sped up, but we're starting to try all sorts of Rowhammer patterns. And this will take a while because the pattern not only has to actually cause a bit flip, it actually has to flip the bit in the right direction, right? We have to actually change a 1 into a 0 or vice versa. And now this pattern that we've just scheduled means that we've just tried, okay, we found a reliable flip, and now we're going to try to see if this flip results in a key that we can factorize. This happens in the background. And in the meantime, because like it's not guaranteed that this will work, so we'll just continue searching for all sorts of different patterns, and we'll also schedule those if they're interesting. This takes a while, and you can see the longer log messages. Right. And now, what you see here is an OpenSSH private key, which means that the key that we scheduled, key number 5, was a public key that, when we applied the bit flip, we could actually factorize the modulus of, and therefore we could recreate a private key. And this is the private key that we've generated. Now, we basically have our ingredients, right? We have a blacksmith pattern, we have that we can apply to the public key. And if we apply that pattern, then a bit in the public key will flip in such a way that the modulus will change, and that we can factorize that modulus, and that we can generate a private key. Now, what's next on our list of tasks is we have to get the public key into memory, and we have to also get the victim VM to get this key into memory. And then after that, it's just waiting a little until KSM has had a chance to look at both pages and to merge the pages so that we control physical memory. So we are just preparing to deduplicate the page. It takes a while until KSM has finished its pass around all memory. Okay, so now we've deduplicated the page and we've applied the bit flip. And now we are going to have to wait until the changes is also picked up by the victim. Again, some more waiting until KSM is done. Okay, and now what you can see here in the log messages is that we found that the flip we found essentially is saying, okay, we are expecting the flip we found to flip a J into an N in the key. And if we just continue the video for a moment, you'll see that this is exactly what happens to the public key. Right, and what you'll notice here is we've tried the original, so the undamaged private key on the victim VM, but now it's rejected its own private key because it no longer corresponds to our public key that we've applied the bit flip to. And finally, what you see here, I'll continue the video until it highlights the change, is that the J has indeed turned into an N, and that we've managed to use this key to gain access to the victim VM, thereby completing the end-to-end exploit. Okay. That's it from our side. Are there any questions?
Hi. So my question is KSM really enabled in production? Because I remember that KSM had a lot of problems even before Rowhammer, like the old flash and reload can be used to leak the accessed patterns. So I thought people are not using it.
At time of the publication of the paper, it used to be, right? This serves as an example, but in security critical context, right, the recommendation has long since been to disable it in its entirety, or at least to consider alternatives.
You know, like, for example, how does it look in cloud providers, like the popular ones, or?
I can only say that at the time of publication of the paper, it was widely used, even in public cloud providers.
Okay.
And I would assume, given, right, the security implications, that its users have since been discontinued, but I can't say for certain.
Okay, that's worrying.
Again, probably, but I don't know for sure.
Hello, hi. Thank you for the remake of the Usenix presentation. It's nice to have it live again. So the question is the following. How much time do you have before the public key that you modified gets back to the original? Because, I mean, the file is in RAM. And basically, when you forge the new private key, and then you have a window of time, and then it's going to roll back to the old one. So how do you guys develop the experiment to make it work?
Well, yes, you're right, because right, the change happens in RAM, and specifically it happens in RAM because the victim key is in the Linux page cache. I can't give you an accurate number on exactly how long it would remain in the page cache, but from my own observations, I'll say at least a minute.
That's right? A lot of time. Yeah.
And we've seen successes up until quite a long time afterwards. And you have to remember that the Linux page cache, if I'm not mistaken, uses basically the remainder of basically all your unused DRAM, right? So if you don't have a lot of I/O going on, a lot of file reading going on or file writing going on, then my expectation would be, yes, it would remain there for quite a long time.
It's dangerous.
Yeah, just to add on that. Yeah, I think so. Actually, it will last until it is evicted. So if you are not under memory pressure, I think it will last there for some minutes or who knows. Yeah, I have a couple of questions probably. Sure. So I think this only applies to those hypervisors that do this memory deduplication. But I don't actually know, besides KVM, did you try the others? I mean, Xen, whatever.
No, I don't. I can't speak for the original. I don't think they did, but yeah, I think they stuck to KVM as an example of the exploit.
Okay, thanks. And yeah, so basically this is exploiting the fact that the data is still in the page cache, in the Linux page cache. So I guess if the target process just bypasses the cache, like opening the file with direct flag or something, this would probably alleviate the issue, I think. But yeah, just to comment on that.
Yes, but if you prevent it from getting into memory in its entirety, right, but you need, if you remove it from memory, right, after you're done with it, probably, like they would have a timing issue, probably, right? Mm-hmm. If you flush it immediately afterwards, for example, but yeah, empty rising here, right? So
yeah. So yeah, thanks again for the talk. Very interesting.
Other questions? Okay, so thanks for the talk, and yeah, that's it.